Good morning. Last time I was started the semiconductor digital ICs, that is chapter number 3 from paper 2. We saw the classification of ICs, bipolar and unipolar, okay, saturated and non-saturated. Then after that we saw the characteristics of ICs, there is propagation delay and power dissipation. We also saw the figure of merit, fan in and fan out. Okay, so this is fan in, this fan out. So here we also saw the current and voltage parameter. Then we saw the input and output profile for the transistor logic ICs, TTL. Okay, so profile means how that considered as a high or low voltage, how it generates the high voltage and low voltage, that gives the level for the high and low consideration for input and output. That is nothing but a input output profile. Okay, then next one we consider, we also saw the noise immunity. Noise immunity means the tolerable signal which is induced over these lines for high state and low state, that is operating. Then after that, operating temperature we saw. Then the different logic families also for the TTL. For TTL there are different types of circuits: saturated, standard, low power, high speed, Schottky TTL, and low power Schottky. So these are the types of TTL: standard, low power, high speed, Schottky TTL, low power Schottky TTL. Okay, so these are the types. And again, last time we saw the NAND gate circuit. Okay, so these are the multi-emitter transistor used at the input. This is a transistor, these are the NPN transistor. Okay, so this arrangement is known as totem pole arrangement. Okay, so this diode is used and this transistor is on state. You have to prevent to turn on this transistor, so that's why we are using the diode. What is the use of this? So just you have to remember this. Okay, because of using this, when this transistor is in on state, it prevent to turn on. When it is on, it prevent to turn on by this diode. So these are connected like capacitors. Whatever the ringings or unwanted change, that is grounded. So these are acts like a capacitors, diode D1 and D2. Okay, so this is the NAND gate. Last time we also discussed case 1 and case 2. In case 1 you have to consider this one, you have to consider these 3 states for case 1, and we have to consider this as a case 2, because all these are having one output. So one output means this remains in off state, this is in on state. Okay, so how it turn on and how it remains off, that is given by the transistor conditions. Okay, and finally when it is 0, output is 0 means this is turn on, and by using this diode it will prevent to turn on, it remains in a off state. Okay, so this is case 2. So we know the functions of diodes now. So then we are going to see the TTL NOR gate. In this TTL NOR gate, the circuit is same. Okay, there is a little bit change. We use different inputs with the different transistor. We are not going to use a multi-emitters transistor. So here we use the, for 2 inputs we use 2 such transistors. Okay, so okay, so this is another, we are using other transistor for this, for another input. So here we use this is, and we are using also diode D in a reverse bias, so that whatever the unwanted transistor will grounded. Okay, input, and this is the input. Okay, and there is another change is we use these transistors with a parallel another transistor, okay, with the same input. Okay, so it is a parallel transistor. So these two transistors are connected in a parallel. So collector is connected to connector, so this emitter is connected to emitter, and this transistor is driven by the transistor this, okay, collector of this one. So we named these transistors are T1, then this is T2, then this is T3, T4, then T5 and T6. I am naming these transistors similar to in a textbook because there should not be problem after understanding this diagram. Okay, there is no conflict, so that's why I am using the same numbers. So we also consider case 1 and case 2. So we know the NOR gate output. So here inputs are A and B, output is Y. Then you should know the conditions of transistors. Okay, so transistors T1, T2, T3, T4, T5 and T6. So we are going to consider the conditions of the transistor. So input may be 0 0, 0 1, 1 0 and 1 1. So output is for 1 0 0 and remain 0 for the remaining states. So we consider the case 1 and case 2. So this is a case 1 and this is a case 2. Okay, so this is considered common case 2 and this is a case 1. So now discuss what happened in case 1. Okay, so case 1 means this one. Okay, so for this case 1, if we apply 0 0, so emitter is low state, these two transistors will turn on. Okay, you should know that when it will turn on when emitter is at 0. So these base are already connected to high state, high voltage, therefore by connecting this 0, these two transistors will turn on. When transistor is on, collector voltages are low. As collector voltages are low, this transistor goes into off state. Both the transistors are off. Okay, because when transistor will turn on, collector voltage drops, so base also drops. So here also base drops. So because of that, as base voltage of this transistor and this transistor decreases, because of collector voltage is low, here collector voltage is low because of this on state. Okay, so you should know the working of a transistor. So T2 and T6 both are in off state. So as these two are off state, the high voltage is applied here. Okay, so high voltage is applied here, and this because of both the off state, so there is no current to these transistors, so this voltage is low state. So because of this low, this transistor is in off state. Okay, and this transistor, because of high voltage is given to the base of this T3, it will turn on. Okay, so as this will turn on, the current flows to this transistor diode and you will get the high voltage. There is no current sinking through this transistor, so it is sourcing now, so you will get high voltage. So this is the first state. Okay, in 0 0 you will get high state. Okay, So just you have to write this condition. So now T1 on, then T2 off, then T3 on, then T4 off, then T6 also off, and T5 is in on state. Okay, so by considering this, you have to write on and off states. So this is for case 1, and you have to consider case 2. Case 2, it is simple working. In case 2, in any state 0 1 1 0 or 1 1. Okay, so for the 0 1, if you apply 0 and this is 1, if this 0 this is 1, so this transistor is turned on, this transistor will turn off. Fine. When it is 0, it will turn on. If it is 1, it will turn off. When it is turned on, this voltage, collector voltage is low. When it is off, collector voltage is high, so it will turn on and it will turn off. So if we consider this state, so for this 0 1, it is clear that T2 will turn off and T6 will turn on. Okay, if this 1 0 state, if A is 1 and B is 0, in this state it will turn on and this will turn off. When it is turned off, it will turn on, because when it is off, the collector voltage is high and it will turn on. Okay, so this will turn on and this will turn off. In this state 1 1, so both, because of A1 it will turn off, because of B1 it will turn off. Both the transistor will turn off, collector voltages are high, and because of that both the transistors will turn on. Okay, so if we summarize these 3 conditions, so I can say at every state one of the transistor of this parallel condition, okay, one of the transistor of this parallel connection will turn on or both will turn on. Okay, for the 0 1, for the 0 1 state, this T6 will turn on. For the 1 0 state, this T2 will turn on, and for 1 1 state both will turn on. Okay, so in these, if we summarize these 3 conditions, we get the result. Now this result, if this will turn on or this will turn on or both will turn on, in every case, as the transistor, one of the transistor or both transistor will turn on, the current flows through this transistor. First condition, current flows through this one. In second condition, current flows through this one. In 1 1 state, the current flows in both the transistors. As this will turn on, current flows here. As this will turn on, current flows here, or both will turn on, current flows in both the transistors. Okay, so if we summarize these 3 conditions, so because of this condition, this will on or this will on or both will on, in that case this collector voltage goes to low now. So here for these 3 cases, collector voltage is low, and as current flows through these transistors and generates the voltage across this resistor, so there is a high. So in all these 3 cases it remains same. Okay, so because of this high, it will turn on. Because of this high, it will turn on, and because of this low, it will turn off. Okay, so always for these 3 cases, the T3 will turn off and T4 will turn on. So this remains low and this remains high. So there may be one of the or both the transistor is in on state. Okay, so this low means this off, this high now means this will turn on. So whatever the voltage at this point is grounded by this T4, the total voltage is grounded, and this diode also will so as this will off, sorry, as this will on, T4 will on, this diode prevents to turn on this T3, which will remains in off state though the voltage is dropped. So now this voltage is low. Okay, so for these three states, okay, so this T3 will turn off, okay, and this T4 will turn on. So this remains same, okay, off, here on and on, this remains stable, so there will not change at the output. Okay, so this when A is 0 and B is 1, so this T3 will turn on, okay, as T1 will turn on, T2 will turn off. As here, because of this one, T5 will turn off and T6 will turn on. Okay, so as 1 0, for 1 0, if this is 1 and this is 0, it will turn off and it will turn off. So T3 will now turn off and T5 now it will turn on. Okay, as T1 will turn off, its collector voltage high and T2 will turn on now. Okay, so here because of this is on state, collector decreases and this is goes into off state. Okay, so after that for 1 1, so for 1 1 both the transistors remains in off state, both the transistor remains in on state. So this remains in off and T5 also remains in off. Okay, and because of that it will turn on and this will turn on. So this state, so these two states defines the output. Okay, for first on and off condition it will on, so when T3 off and T4 on, so it remains same and we'll get the output voltage 0, because as T4 will turn on, the voltage drops to 0 through this transistor. Okay, so this is a TTL NOR gate. Okay, so most important point this one. So next, so this is a totem pole arrangement. Okay, this is a totem pole arrangement, but in some cases you have to omit this transistor, this diode and this resistor. Okay, then whatever the remaining output state remains only this and this one. Okay, so finally, so output circuit remains only this one. Okay, so this is the T4 and here output. So whatever the remaining circuit is same, remains same. For TTL NAND gate or TTL NOR gate, this type of connection is known as open collector output. Okay, open collector output. So open collector output. So this output is open, there is no any connection with this output terminal. Okay, so this is known as open collector output. So how we are going to see the output, observe the output? Then in that case you need to connect a resistance R, which is called as pull-up resistor. What is known as pull-up resistor from VCC. Okay, so because of this simple resistor connection, you have to connect it externally. You need to connect it externally, which is not in IC. So it is known as pull-up resistor, and by connecting this you can observe the output as same as that of previous. Okay, so this is the open collector arrangement. So only you have to connect the external resistor. So what is the advantage of this connection? So there is a main advantage is this circuit is reduced. We don't require this transistor T3 and diode. We don't require this transistor T3, diode and resistor. So this circuit is minimized, number of transistors are decreases. Okay, so this is the main advantage. And another advantage is because of this open collector, you consider this one, this circuit. Okay, so this all the outputs of these NAND gates are connected to the input of OR gate. So in this case we don't require to connect an OR gate, so just we use a common pull-up resistor and all the outputs of these open collector TTL combined together, and that is connect to the that resistor, and it will form a OR circuit. Okay, we don't require this OR gate, so just you have to connect the simultaneously. This is known as wired OR. Okay, so it is known as wired OR. So this is another advantage. First advantage is circuit is minimized. Second advantage is for this wired OR. Okay, wired OR, so that we avoid this OR gate. So this is the advantage. Okay, so the disadvantage is it increases propagation delay because we are connecting a single resistor here, so it is also resulting in a low speed. So this is a disadvantage of this wired OR. Advantage is circuit is wireless circuit, and there is a elimination of this OR operation. By connecting single wire we can perform this OR operation. Okay, so this is the open collector TTL circuit arrangement. Okay, now we are going to see here the tri-state logic. So we know there are two states, 0 and 1, high and low. So there is another state, that is high impedance state. So that is called as a third state. So we are going to consider here the what is the third state, what is tri-state logic. So here tri-stated is a high impedance state. Okay, so this is the inverter, one input and one output. So there is another second input, that is third terminal. So second input, which is enable. So if this enable input is in high state, the inverter works normally. If 0 is applied, you will get 1. If 1 is applied, you will get 0. If 0 is applied, you will get 1, and if 1 is applied, you will get 0 here. So now this inverter works normally if this enable is 1. If this enable is 1, okay, inverter works normally. If 0 applied, we will get 1. If 1 applied, you will get 0. But this if enable is at 0 state, it is tri-stated. Tri-stated means high impedance state. Whatever may be the input, output remains in a same state. If you apply 0 or if you apply 1, okay, if you apply 0 or 1, there is no change at the output, that is a tri-state. It is high impedance state. Okay, so it will not respond for input 0 and 1 also. If enable input is 0, so it is known as a tri-stated logic. So this is the inverter and this is a buffer. Okay, so this is buffer. Buffer means what? It has a same input, that of the output. Output remains equal to the input. If you apply the input state, you will get the, if you apply 0, you will get 0. If you apply 1, you will get 1. So this enable, okay, when we apply enable 0, then output remains same without considering the input. If we apply enable 1, then output follows the input, output equal to input. That is known as buffer state. Okay, so afterward we are going to see what is the use of this tri-state logic. Okay, so in the tri-state logic the diagram is given this. Okay, so we know that this is a TTL NAND gate diagram, so there is some changes. Okay, so we need another transistor which is connected here. Okay, and this one. So we need to connect the base at this collector. We need to connect a, so there is jumper, there is no connection. So to the anode of this diode, and this is connected to this emitter terminal, and this is called as enable or control. Okay, this is known as enable or control, and this is a data input A. Okay, so if this enable is in 0 state, let us see what happens when enable is in 0 state. If enable is 0, this diode will turn on, forward biased. Why it is forward biased? Because anode is connected to the high potential through the resistor and 0 is applied to the cathode, so this becomes forward biased. As this will be forward biased, this collector voltage maintain at a low state voltage. Okay, why? Because whatever the voltage at this point, whatever the condition it may be, so we don't bother about the condition of this transistor or this transistor. Okay, so with this enable is 0, the diode will forward biases and it drops the voltage at the collector of this transistor. Okay, as this collector voltage is low, it is applied to this base of the transistor, so it will remains in off state. This will maintain this status to off. Okay, as because of that, as this is low, means transistor is turned off state, so there is a high voltage. Because of this I, it will turn on. Okay, so when the enable is 0, this state remains fixed. These two transistors are turned off and this will turn on. So because of that, you will get y equal to always 0, that is tri-stated. When we change the A input, there is no effect on the output, so that is known as tri-stated. So when enable is 0, okay, so this state remains in the same state and is called as tri-state. Okay, high impedance state, that is a tri-state, high impedance state. Okay, so as if enable is in one state, okay, now consider enable is in one state, and this, because of this one state, the diode is reverse biased now. Okay, so I am circling this state because these are the same condition. As this is 1, enable is 1, the diode is in reverse biased, and because of this diode reverse bias, its role in the circuit is over now. Okay, its role, diode's role in the circuit is over now. So now it depends on this A state. Okay, if A is 0, it will turn off, then it will turn on. So because of this on state, these two are off, and because of this on state, the current flows through this and it will turn on this. Okay, so like that, because of this turn on state, you will get the 0. Okay, correct? Sorry, if this will turn, if it is 0, it will turn on. Sorry, there is a little bit mistake. Okay, it will turn on. As it will turn on, it remains off. As it will off, there high, if this voltage goes high, as it goes high, these will turn on, this will turn on also. Current flows through this. As it is high, it is voltage is low, so it will turn off. You will get one step. Sorry, there is a little bit mistake is here. Sorry. So this is off. Because of this 0, it will turn on. This will off. High voltage, it will turn on. So because of this off condition, there is no current, and it will turn low voltage, it will turn off. So you will, because of this high state, whatever the current will get the high voltage. Okay, so this is a tri-state logic. If we apply 1 now, the conditions will get reversed. If this 1, it becomes off, it will on, current flows through this, you get the high voltage and it will turn on, you will get the output 0. So all these conditions will reverse if A is equal to 1. So this is known as a tri-state logic. Okay, so this tri-state logic is used in the microprocessor circuit. In that case, this is the data flow, this is the input data. Okay, and suppose we want to route the data to here, this to here. In that case, you enables both these so that it is routed here. Okay, if you want to route this incoming data to here, then you made these to enable so that this data will routed to here. Okay, so such type of applications we use the tri-state logic circuit. Okay, so now we are going to stop here.